Chapter 7 is titled Exponential and Logarithmic Functions. We're going to start off by combining lessons 7.1 and 2, looking at exponential, growth, and decay functions. For an exponential function, we have the form y equals a times b to the x power. This is different than an exponential, like a rational exponent. This is an exponential function because x is the exponent. So we're not looking at just x as a base, we're looking at x as the exponent. A would represent the original amount in a growth or decay model, maybe like the population of a city in a given year. For b to be a growth factor, the value for b would be greater than 1. X typically would represent the time, and y would be the new amount after a given period of time. Over on the right, notice we have the graph for y equals ab to the x when b is greater than 1. This is an exponential growth model. It would have arrows at the top and over on that left-hand side. At 0, the base would cancel out. B to the 0 power is 1, and it would cross the y-axis at a, at that original amount. You'll notice as x goes to the left, the graph gets lower and lower and lower, but it actually isn't going to cross over the x-axis. The x-axis is a boundary line that it doesn't cross over. We had that back when we covered conic sections. That's known as an asymptote. The difference between a growth and decay model is the value of that b, or base. If you have a decay function, we still have our a value, we still have x, we still have y, and what makes b unique is it's between 0 and 1. So that would mean it's a fraction. Notice the graph looks similar to the graph up above. We'll have our arrow at the top, and now our arrow goes to the right. It still crosses the y-axis at whatever your a value is, but it's kind of in reverse. As x gets smaller, the function gets bigger. This means this function reflects over the y-axis. What we can do with these values is we can perform transformations on them. For example, if a is negative, the graph would reflect over the x-axis. Hopefully you can get that to fit in there. There we go. Reflects over the x-axis. If something's being added or subtracted to the function after the base, the graph would move up or down. By that k value. And then if we have something being added or subtracted to the actual exponent, the graph would move left or right. And if you remember, what happens with anything with x, it goes in the opposite direction. So if it's a subtraction problem, it would move to the right where you think it would move to the left, and vice versa. So we'll put that in parentheses here, in the opposite direction. Okay. One other thing to note with this part right here, if you have that k value that moves the entire graph up or down, that can also change the asymptote. So it may not be the x-axis if you move the whole thing up or down. All right, let's go ahead and sketch some graphs. First, let's sketch the graph of y equals negative 2 to the x power. The first thing you want to consider is putting it in the form y equals a times b to the x power. In order to have a function that's an exponential function, the base itself technically can't be negative. In this example, y equals negative 2 to the x, notice the negative isn't in parentheses. What this actually means is that the a value is negative 1, and the base is 2 to the x power. Since a is negative 1, we know that this graph should reflect over the x-axis. The curve will actually open upside down. So let's see how that's going to work. Go ahead and make a table, and you may either want a calculator or your power chart. We're going to pick values for x, plug it in for the exponent, and see what our y values will equal. And then we'll graph them. It's always a nice idea to start right at the center when x equals 0. If you plug in 0 for x, 2 to the 0 power is 1. Remember, anything to the 0 power is 1. That was one of our exponent properties from chapter 5. But when you multiply that by the a value, -1, it makes our answer negative. So you'll notice all of our answers are going to end up being negative because of that -1 out in front. If I plug in 1 for x, 2 to the first power is 1, but multiply that by that -1 out in front, changes it to -2. If I go one more to the right, 2 squared is 4, but then that negative will make it -4. 2 cubed is 8, but then that makes that -8. And if I go 2 to the 4th power, that's an 8 right there, sorry about that. Whoa, it is an 8, trust me. If I go 2 to the 4th power, that's going to put me at 16, and that'll put us off the graph. Let's go in the other direction. Watch what happens when we pick a negative exponent. If I plug in -1, 2 to the -1, you'd have to take the reciprocal of 2, would become 1/2. And then the negative out in front would make that -1/2. I'm going to have to draw that on the side right there to get that to fit. I'm going to plot one more point, -2. If we raise 2 to the -2 power, we have to take the reciprocal. 1 over 2 to the +2 power would be 1/4. Whoa, times -1 is -1/4. That's getting pretty small. Let's go ahead and sketch our graph and see what happens when we plot those ordered pairs. We'll start with 0, -1 down below. And then as I go to the right, 1, -2, 2, -4. Do you see how it's not a linear function right now? There's a little bit of a curve to those points. And then when I go over to 3, we drop all the way down to -8. So you can really see that curve starting to happen. And then check this out. If we go to -1, it only drops down to -1/2. There's really a turn starting to happen there. And then at -2, just barely below the x-axis at -1/4. We're still going to have, hi Diesel, that's my cat Diesel. We're still going to have the asymptote on the x-axis. So what I'm going to do is kind of like what we did with hyperbolas back in chapter 9. I'm going to draw kind of that boundary line in right there. We don't want to cross over that line. And then as we sketch plot the curve kind of through those points, let me see if I can get that to even happen here. We're super, super close to that x-axis, and then all of a sudden we drop down really, really fast through those y values. And there's your exponential function, y equals -2 to the x. Let's try the next one. Our next function, y equals 2 times 3 to the x plus 1 power. Notice there's no negative on this one, so we're not going to reflect over the x-axis like the last one. Our base is +3, so this is going to be a growth function, and the a value is 2. But what's going to make this one unique is that x plus 1. Whenever anything's being added or subtracted to x, the graph is going to move in the other direction. So the entire graph is going to move left 1 unit because it's plus in the equation. So left 1 unit. That's going to affect how we make our table, and I'll show you what I mean by that. If we start with our x and y axis, typically I would say start at 0, like we did on the last problem. But if it says move 1 unit to the left, I'm actually going to start at -1. I want to kind of follow the pattern and see where that curve takes us. If we plug in -1 for x, we just have to think order of operations. -1 plus 1 for the exponent is 0, and 3 to the 0 power is 1. 1 times 2 is 2. All right, now I'm going to go to 0 and see what happens. If I plug in 0 for x, 0 plus 1 is 1. 3 to the first power is 3, and then 2 times 3 is 6. That's getting big pretty fast. And then if I pick 2, watch this. Or not 2, sorry, 1. Watch this. If we pick 1 for x, 1 plus 1 is 2, okay? 3 squared goes up to 9. 9 times 2 is already 18. Whoa, that's already way off our graph. So now we're going to have to go in the other direction. We went to -1 at first, so let's go one more to the left and see what happens. Let's go to -2. If you plug in -2 for x, -2 plus 1 is -1. 3 to the -1 would be 1/3. 1/3 times 2 drops all the way down to 2/3. So we're not going to really have a lot to plot on this graph. We're getting pretty close to that y or that x-axis already. Let's try one more and see if we can get one more to fit nicely on our coordinate system. If we plug in 3 for x, -3, -3 plus 1 is -2. 3 to the negative 2 power would be 1 over 3 squared, which is 1/9. Multiply that by the 2 out in front, that becomes 2/9. That's pretty small. I think that's probably as good as we're going to get. If we graph negative 1, 2, and then 0 all the way up to 6, 1/18 is way up here somewhere. This is way off of our graph. If we go to the other side, negative 2, it's all the way down to 2/3, so just right below that x-axis, or the 1 on the y-axis. And then at negative 3, down even smaller. So you'll notice once again, just like that last graph, we're going to have that asymptote. So let's draw in that dashed boundary line just to make sure we don't cross over it. And then we'll connect our dots to create that exponential growth function. So small, teeny, 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 tiny on the left, and then all of a sudden just gets super big, really fast. Whoa, sorry, that graph got a little crazy on me. And that's not much better. Sorry, let's see. We'll just try to make that one look a little bit nicer there, I guess. There we go. We'll go with that. How about that, you guys? And there's our exponential growth function. Y equals 2 times 3 to the x plus 1 power. All right, let's do one more. This one's pulling out all the stops. Take a look at what's going on here. We have y equals negative 1/2 to the x minus 3 power plus 2. Wow. The only thing we're missing is the defined a value. Notice 1/2 is in the parentheses, so that's the b value, but that negative out in front, that means a is negative 1. Let's make sure to make that clear, and that way we'll recognize some things that are going to happen to the graph because of it. We also have x minus 3, so that's going to do something to the graph, and we haven't had anything added after, so we have that plus 2. There's a lot that's going to happen to the shape of this graph based on kind of what the original basic growth and decay models looked like. We know a is negative 1. That means the graph is going to reflect over the x-axis. Let's jot that down to make sure we remember that in our table. So it's going to reflect over the x-axis. The b, the base, is 1/2, so that's a decay function. So remember, that's going to look like it reflects over the y-axis. The x minus 3, remember, it's going to move it right or left, but kind of backwards of what we think. This is going to move 3 to the right. And then that plus 2 is going to move it up or down the same amount. So that's going to move everything up 2 units. It's also going to change our asymptote for x. Whoa, all right. Who's ready to make a table? I know I am. Woohoo, there we go. All right, thinking about how to create our table from these changes that are happening in the equation. The exponent's going to kind of drive where we start. Remember before how we had x plus 1, so we started at negative 1? Here we have x minus 3, which means kind of the whole curve is going to shift 3 to the right. So let's start at positive 3 instead of 0 and see what happens to our graph. All right, if we do 3 minus 3 for the x exponent, 3 minus 3 would be 0. 1/2 to the 0 power is 1. And then we have to multiply it by negative 1, which would be negative 1, and then add 2. If we do all that, we should get an output of 1. So think through that again, everybody. 3 minus 3 as the exponent would be 0. 1/2 to the 0 power, it becomes 1, times that negative 1 out in front stays negative 1 plus 2. So we get an ordered pair of 3, 1. If we go 1 to the right, plug in 4. 4 minus 3 is 1. 1/2 to the first power is 1/2. Times negative 1 would be negative 1/2. Plus 2 would be 1.5 or 1.5. So it's getting a little bit bigger. Keep going. If we plug in 5, 5 minus 3 is 2. If we square 1/2, we're going to get 1/4. And if we have 1/4 times negative 1, that's negative 1/4. Plus 2 would be 1 3/4 or 1.75. So we're getting bigger, but we're kind of approaching that 2 at a slower rate. So do you see how it's getting closer to 2, but not really, really fast? Let's see what happens if we go in the other direction. We started at 3. So if I go to 2, 2 minus 3 is negative 1 for the exponent. If we have 1/2 to the negative 1 power, we have to take the reciprocal of the base. That would give us 2. times the negative 1 out in front would be negative 2, and then plus 2 would be 0. Let's go one more to the left at 1. 1 minus 3 for the exponent would be negative 2. 1/2 to the negative 2 power, we have to take the reciprocal, would be 2 squared, which would become 4, times the negative 1 out in front makes that negative 4, and then plus 2 becomes negative 2. All right, let's try 0. We'll try 0, we'll see what happens, and I think that'll be enough for us to plot on our graph. If we plug in 0, 0 minus 3 is negative 3. 1/2 to the negative 3 power would be the same as 2 over 1 to the positive 3 power, which is 8. Negative 1 times 8 is negative 8, plus 2 is negative 6. All right, let's plot these points and see if we need to draw in our asymptote so that we don't cross over it. 3, 1 is over here kind of on the right. 4, 1.5, so kind of in the middle. 5, 1.75. Do you see how we're getting pretty close to 2 on the y-axis? Let's go ahead and draw in that asymptote right at 2, since everything moved up 2 units, just to make sure we don't cross over it. All right, let's get the rest of those points and be done with this part of the lesson. If we go back to 2 on the x-axis, we're at 0. 1 drops us down to negative 2, and 0 dropped us all the way down to 6. Do you see that curve starting to take shape for this exponential decay function? Remember, the a value reflects it over the x-axis, and the 1/2 reflect it technically over the y-axis. If we draw a curve through these points, it's going to kind of come up, and it's going to plateau pretty quickly right along, whoop, don't get too close, right along to that asymptote on the line y equals 2. And there's your exponential decay function. This is it for the first part of 7.1 and 7.2.